Hello everyone. Today we will discuss section 14.6, the directional derivatives and the gradient vector. I don't know how this is going to work out, but I will try my best to help you out with some lecture notes. Will I be able to do it all through the semester? I don't know. Will I be able to do for all the sections from this point forward? I don't know. But will I try? I will try. So let's start with 14.6, which is directional derivatives and the gradient vector. So I will try to go as slow as possible, but because this is not a classroom setting, I don't know if you have any questions at any particular step or not. Of course, please feel free to email me. Email me when you have questions. Again, this is section 14.6 on directional derivatives and gradient vector. The goal of this section is actually linked to the next section. The next section is on finding the maximum and minimum. So for that, to find the maximum and the minimum, we need gradient vector. To find the gradient vector, we need the directional derivative. So it's backwards, okay? So the directional derivatives is the partial derivatives. So here we are defining the partial derivative of f with respect to x. That means z is a function of x and y, and partial derivative of f with respect to x is given as this, and partial derivative of y with respect to a partial derivative of f with respect to y is given as this in the limit case. If the limit exists, then the partial derivatives exist. If the limit does not exist, then the partial derivatives do not exist. I'm hoping that it will be very clear to you. Now you can also write this as, let's say if I have something like fx of xy, then I can write this as limit h going to 0, f of x plus h, x plus h and a y minus f of xy divided by h, and I can also write fy of xy as limit h going to 0, f of x and y plus h minus f of xy all over h. Okay, now these represent the rates of change of the function z in the direction of x and also in the direction of y. And now the direction of x is the direction of y, and the direction of y is the direction of j. So it represents the rates of change along this is along the x-axis or x direction. This is the rates of change along the y-axis or the y direction, or you can write this as along I vector because I is along the x-axis, or you can write this as along the rate of change along the j vector because j is along the y-axis. Okay, now the directional derivative of the function f at x naught y naught in the direction of a unit vector uab is represented by the directional derivative of f in the direction of u is given by that. So directional derivative of f, that is represented as the f in the direction of u in the direction of unit vector u is a b is given by duf. Okay, and at the point x naught y naught, at x naught y naught is given by x naught y naught. Now please see that u is a unit vector, so that means magnitude of u is going to be our absolute value of u is going to be 1. So that means magnitude or absolute value of AB is going to be 1 as well. Is that clear? Now you can see that in the directional derivative, that means there is some component of change along the a-axis, there is some component of change along the b-axis. That's why the change is along the x-axis and also the y-axis. It's put together. Okay. Now I hope that is clear to you as well. Now how would we do that? If f is differentiable function of x and y, f has a directional derivative in the direction of any vector u, a, b, and du f of x, y is fx y of a plus fy of x, y, b. If u is if u makes an angle theta with the positive x-axis, then we can write u is cosine theta, sine theta. Now let's prove it. I mean, it's not really a proof in the real sense, but as semi-proof kind of a thing. Let's define a function g, like g of h, as f of x naught plus ah plus and y naught plus bh. Okay. Now let's say I want to find now if g of 0 would be, that means I'm substituting h is 0. If h is 0, then g of 0 would be f of x naught plus a times 0 and y naught plus b times 0. So that's going to be f of x naught and y naught. Okay. Then I want to find g of h minus g of 0 divided by h minus 0. So that would give me what? It would give me f of x naught plus ah y naught plus bh minus f of x naught y naught all over h. Okay. Then if I upon taking limit h going to 0 on both sides, I would get this to be limit h going to 0 on both sides here, right? So then this is nothing but from calc 1 we know that this is g prime h, and from calc 3 in the previous page we did, this is a directional derivative of the f of f in the direction of the unit vector u at the point x naught y naught. Okay, so that's what you would write that. Now I mean, you know, but we can also use the chain rule and see what happens. This is one way. Then this is one thing. Now let's consider again. I mean, recall what is your your gh. Your gh is really f of x naught plus ah and y naught plus bh. Now if you want to find g prime of h, that means you're gonna g prime of h, that means you're gonna use the chain rule here. That means this is gonna be I mean do f partial f partial x times partial x partial h plus partial f partial y times partial y partial h. Why? Because I mean, you know, f is a function of x and y, and x is a function of h, y depends on h. That's why you're using the chain rule. Now if I do that, I'm going to get this g prime of h is going to be partial f partial x times partial x partial h would be, I mean, you know, if you recall, x is going to be x naught plus ah. So partial x partial h is going to be just a, so times a plus partial f partial y, and you know that y is going to be y naught plus ah. Y equals y naught plus ah, that's going to be partial y partial h is going to be sorry, bh here, that's going to be b, so that's going to be b here. So that means you get g prime, I hope you can see it from here clearly, g prime of h is going to be, you can also write it as a dot product partial f partial x times partial f partial y, and the dot product with a and b. So this is going to be really, you can write this as fx fy dot a and b. So this is going to be nothing but this is going to be nothing but from here it's going to be nothing but the directional derivative of the function f in the direction of unit vector u in the direction of the unit vector u at the point x naught y naught will be that. So you can write this as partial derivative of f in the direction of the unit vector at the point x naught y naught is going to be fx fy dot product with ab, or in other words it's going to be fx at x naught y naught times a plus fy at x naught y naught times b. Now in the future we're going to refer to this as a gradient vector. Okay, I'm just jumping ahead so that you know why I'm doing all this. Like, you know, the directional derivatives are connected with the gradient, and the gradient is connected with the maximum and minimum, which you will see in the next section. Hopefully I'll make a video on that as well. It's already 10 minutes long and we're only 2 slides into the lecture notes. Okay, now let's see some example. We want to find the directional derivative of the function f in the direction of u, unit vector u, if the given function is this, if the function is given like that, and u is the unit vector given by the angle theta, and that is that. So we want to find the directional derivative of the function f in the direction of u at the point 1, 2. So let's find the partial derivative of fx. So that means you're going to differentiate this with respect to x. So that's going to be x cubed minus 3xy plus 4y squared. So that's going to be what? It's going to be whatever that is. It's going to be 3x squared minus 3y. Okay, and then you want to find the partial derivative of f with respect to y. That's going to be, you're going to differentiate with respect to y. So x cubed minus 3xy plus 4y squared. So that's going to be, when you differentiate it, you get negative 3x plus 8y. Okay, I think I'm pretty much there. Correct, I think I'm pretty much there. Now what do? The goal is to find the partial derivative is to find the directional derivative of f in the direction of unit vector u at the point 1, 2. So that means insert at 1, 2, right? So insert x is 1, y is 2. Then what you get is, fx at 1, 2 is going to be it's going to be 3 times 1 squared minus 3 times 2, which is going to be 3 minus 6, which is negative 3. Hopefully I'm on the screen. If I'm not on the screen, God bless us all. The partial derivative of f with respect to y on 1 at 1, 2 is going to be, okay, negative 3 times 1 plus 8 times 2. That's going to be negative 3 plus 16. So 16 minus 3 is going to be 13. So that's going to be the partial derivatives evaluated at 1, 2. Now you want to find what is that? A partial directional derivative of f in the direction of the unit vector u, right? In the direction of the unit vector u at the point 1, 2. And from our previous formula, let me bring that page back. That's the formula that we are really using here. This is the formula that we are really using here. So that's going to be whatever that is going to be. That's going to be fx at 1, 2 times a plus fy at 1, 2 times b, right? I hope you're with me on that. U is gonna be AB. Now I'm gonna give you a big, how do I say it? Now I'm gonna give you a big surprise, okay? AB. But do we know, so let me write this out. This is gonna be the dot product of fx at 1, 2, fy at 1, 2, dot AB, right? So this is a gradient vector, that is your u. We don't know that, right? So this is going to be the partial derivative of f with respect to x is evaluated to be -3, and the partial derivative with respect to whatever that is y with respect to y is evaluated to be 13, and we don't know really AB, but we only know that it is a unit vector, right? That's where it is. So A is going to be along the x-axis, so you are going to say this is A is I cosine theta, so that's going to be A is going to be cosine, theta is going to be pi over 6, and that's going to be square root of 3 over 2. And B is going to be J sine theta, so that's going to be J is 1 unit vector, right? J along the direction of y-axis. Sine theta is going to be sine pi over 6, that's going to be 1/2. So your vector u is going to be square root 3 over 2 and 1/2. You with me on that? But we want to make sure that is this a unit vector? That's what we want to make sure, that this is a unit vector. So when you do that, what is that? Absolute value of u or magnitude of u is going to be what? Square root of 3 over 2 squared plus 1/2 squared. So that's going to be what? Square root of 3 over 4 plus 1/4, and that's going to be 1. So it is a unit vector, so we can just write this as -3 and 13 times whatever that is, square root of 3 over 2 and 1/2. So when you do the dot product, you're going to multiply these two, you're going to multiply those two. So that's going to be -3 square root 3 over 2 plus 13 over 2, and upon adding these two, you get 13 minus 3 square root 3 over 2. I mean, I'm adding means I'm rearranging the terms and subtracting them together to get that. So this is the directional derivative of the function f in the direction of the unit vector u at the point 1, 2. That's how you evaluate the direction vector. I hope this is clear. I have no way to check whether my video is going correctly or not, but I'm assuming that it will all turn out well at the end. Otherwise, I don't know what to say. Okay, so now the gradient vector. Okay, the gradient vector is defined like that. If f is a function of two variables x and y, then the gradient vector of f is the vector function defined by that. This is a Greek alphabet. Sometimes you refer it to it del. So I mean, if you have this, you call it as either del f, or you call this as gradient f, or you call this as grad f. I mean, you know, whichever way you want. I mean, all three mean the same. But what does that mean? So gradient is like a box, okay? So gradient is like a box. So if your function is f of x, y, then you get a vector, some vector, like I don't know how to put it. Yeah, you get fxi plus fyj. Okay, if you put a function fxyz, then you get the output of that would be fxi plus fyj plus fzk. So you see that if you put a function of two variables, you get a two-dimensional vector. If you put a function of three variables, then your output would be a three-dimensional vector. So you can define gradient as a function from Rn to Rn. Okay, so it goes from R squared to, I mean, this is R squared really, and your output is also inside R squared. Here your domain is in R cubed, and your output is also R cubed. So gradient can go from Rn to Rn. If your n is 1, that means then it becomes just a derivative, okay? Then there's no point in using derivative gradient. If your n is 2, then it is like this. If n is 3, like this, then subsequently it happens like that. Okay, so this is what we have seen, the partial derivatives. So you see this was, I mean, if you see the what was that? This was a, I mean, you know, when you define the directional derivatives, I hope I have the page with me. I can go back. You see, when I define the directional derivative of the function f in the direction of the unit vector u at the point x naught, y naught, I got this. This is the gradient. You see that? From directional derivatives you go to the gradient, from gradient you go to the maximum minimum. That's the bigger picture. Okay, let's just get through this and see what happens. Okay, I hope you will enjoy it. Okay, now let's find the gradient of the function f of xy here and then evaluate the gradient at 0, 1. I hope you're all following with me, and let me drink some water right now because I'm feeling thirsty. Okay, now, so to find a gradient, you need a partial derivative fx. So fx at xy is going to be, you're going to differentiate with respect to x, so you get sine x plus e to the xy. So that's going to be what? That's going to be derivative of sine x is cosine x plus derivative of e to the xy is e to the xy times you're going to differentiate xy with respect to x, and y is treated as constant, so y would step out, so you get y e to the xy. I hope you understood that. Fy of xy is going to be, you're going to differentiate d by dy of sine x plus e to the xy. So derivative of sine x is going to be with respect to y is going to be 0 plus, you get e to the xy times the partial derivative with respect to y. Here you would do that, so you get x e to the xy, right? So you want to find a gradient of f xy is going to be you get fx fy, so that's going to be here cosine x plus y e to the xy, and you get x e to the xy, correct? So that's the gradient function. So you see you have let me focus it. Okay, I think it's focusing better. So it's a function of two variables. You got a 2D vector. Do you see that? Now let's evaluate gradient f of 0, 1. So that means you're going to insert x is 0 and y is 1. So you get cosine 0 plus 1 times e to the 0 times 1, and you get x is 0 e to the 1 times 0. So that's going to be cosine 0 is 1 plus this is going to be 1, and that's going to be this is going to be 0, so that's going to be 2, 0. So the gradient is going to be gradient of the function at 0, 1 is 2, 0. Okay, I hope you're clear with that. Okay, now the directional derivative of a differentiable function is given to be that. This is pretty how do I say, this is pretty obvious, right? It was not that big a deal because we did that in the previous what was that in the previous stuff. Why? Because directional derivative of the function f in the direction of u at x naught y naught was given to be what? Is given to be, I think, fx evaluated at x naught y naught times a plus you get fy evaluated at x naught y naught times b, right? So that means when you write it, you can write it as fx x naught y naught and fy at x naught y naught times dot product with a and b. Okay, a and b is the unit vector u. Okay, so this is nothing but, now we know this is a gradient of the function f dot product with u. That's what they're basically saying. Okay, or in other words, it's the gradient of f at x naught y naught and dot u. Okay, because this is at x naught y naught, the gradient is evaluated at x naught y naught. If this was if the directional derivative was evaluated at xy, then the gradient would also be evaluated at xy. If the directional derivative was evaluated at alpha beta, then gradient would also be evaluated at alpha and beta. Okay, so hopefully that is clear. So now let's go ahead and evaluate directional derivative of this function at 2, -1 in the direction of v. Instead of u, we are using instead of u, we are using a function v. That's the only difference. Otherwise, the rest everything is same. First of all, let's see. Magnitude of v is going to be square root of 2 squared plus 5 squared. So that's going to be what? Square root of 29. So this is not a 1. So that means this is not a unit vector. So you want to make it a unit vector, so you divide v divided by magnitude of v. I mean, sometimes I put absolute value, sometimes I put two lines. It both mean the same. So don't get confused by that. Okay, so that means 2i divided by square root of 29 plus 5j divided by square root of 29. This becomes a unit vector. So we are really interested in this. Okay. Now we want to find the directional derivative, right? Directional derivative here, right? First, for that you need fx, so that means partial derivative of this function with respect to x. When you do that, I mean, I'm thinking you want to see this, you want to see me writing this step. I don't know, I'm assuming it. So when you differentiate it, you get 2xy cubed minus 0, so that's going to be 2xy cubed. And you want to find the partial derivative of y, so that's going to be dy, so you get x squared y cubed minus 4y, so that's going to be x squared is treated as constant, and different derivative of y cubed is going to be 3y squared minus 4, so that's going to be, you get 3x squared y squared minus 4, right? So you want to find okay, recall the directional derivative of f at u in the direction of the unit vector v here. Okay, that's not u. And evaluated at 2 and negative 1 is going to be the gradient of the function at 2 and negative 1 dot unit vector with u. Okay, so we want to find a gradient vector. So we want to find fx at 2 and negative 1. So that's going to be 2 times 2 times negative 1 cubed. So that's going to be negative 4. Then you get fy of 2 and negative 1. So that's going to be, what is that? 3 times 2 squared negative 1 squared minus 4. 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. Okay. So now, now you want to find the directional derivative of f in the direction of the unit vector v. Evaluated at 2 negative 1 is going to be the gradient of the function at 2 negative 1 dot product with the unit vector. Okay, so that's going to be what? It's going to be negative 4 and 8 dot, you get 2 divided by square root of 29 and you get 5 divided by square root of 29, right? So what do you get? You get negative 8 divided by square root of 29 plus 8 times 40 is going to be 8 times 5 is 40. 40 divided by square root of 29. Okay. So that would give you 40 minus 8 is going to be 32 divided by square root of 29. Okay. So this is what we use, like directional derivative. That's the key thing. I mean, the takeaway from this problem is this. The directional derivative of the function at a point in the direction of the unit vector is given by the gradient of the function evaluated at the point times the unit dot product with the unit vector, not times. It's a dot product. Remember that. That's the dot product. Okay. That's the big takeaway from this thing. Now it's almost 30 minutes. So for a three-dimensional vector, I mean, it's going to be the same. Or in other words, I mean, you know, we want to find this. This is how it's going to be, and the directional derivative of f in the direction of the unit vector u evaluated at x naught, y naught, z naught is going to be the gradient of the function f evaluated at x naught, y naught, z naught, and the dot product is with the u where u is the unit vector. Okay, and the gradient of I told you, right? I mean, you know, I recall that gradient is like a box. If you have a function f of x, y going in, then your output is going to be fxi. It's a two-dimensional vector, fyg. If your input is a function of three variables, x, y, z, then your gradient is a three-dimensional vector, fxi, fyj plus xzk. That's what they're referring to here. We did that. Okay. Now, I mean, we did this again. I mean, the construction is, I mean, it is very, we did it in a two-dimensional case. Let me show that to you one more time. I mean, here, this is when it was a two-dimensional vector. I mean, f is a function of x and y, and u is a, b. Then what we did was we got this to be fx x naught y naught a plus fy x naught y naught b. That was the directional derivative of f in at x naught y naught in the direction of u. So that's exactly what they're talking about. I mean, you have that. That's what you can write. I mean, directional derivative of f with respect to u at x, y, z is going to be fx a. For simplicity, I'm ignoring that. Fy b. Then you get fz and fc. So that means you write this as fx fy fz dot product with a b c. So this is going to be the gradient of the function f at x y z, and this is going to be e. So again, the same thing. It's really not a big deal. Okay. Where are we? How much? I just want to know. Now, the directional derivative of the differentiable function is this. I mean, I just showed you, right? So that's what it is. I mean, there is nothing really new to it. So we're going to use that. So I'm going to skip it. I just talked to you about it. Now, if the function is given to be that, find a gradient. Of course, here you see function f is a function of three variables, so you're going to get what at R3. I mean, three-dimensional vector. So you want to find fx, and fx is going to be sine yz. Okay. Then you want to find fy. Fy is going to be what? X is treated as constant. Derivative of sine is going to be cosine yz, and derivative of yz is going to be just a z. So so you get x z cosine yz. Okay. Don't distribute z to the z here and make it z squared. That's going to be terrible. Now fz is going to be, you want to differentiate this with respect to z. So x is treated as constant, so that steps out. So you get x. Derivative of sine is cosine yz. And you're going to chain rule. So you're going to differentiate yz with respect to z, and when you differentiate that, you get y. Okay, now don't distribute y to the z. That's totally wrong. So you get xy cosine yz. Okay. So your now gradient of the function f at x, y, z is going to be fxi fyj plus fzk. Okay, and so that means the rate of change along the x-axis is fx. The rate of change along the y-axis of the z component is fy. The rate of change of f along the k component. Right, or along the z-axis is fz. So that's going to be you get sine yz I plus xz cosine yz j plus xy cosine yz k. Okay. So you see, this is a three-dimensional vector. So gradient is a function like from r cubed to r cubed. I don't know if my voice is loud enough or not, but put up with it. Let's see if I can get this nearer to me, so that you can hear me nicely. Oh God. Okay, let's adjust the focus one more time. Okay, so hopefully this is close by and you can hear my voice nicely. I don't know whether you can hear it nicely or not. Okay, now find the directional derivative of the function f. So that means this is the previous problem is gonna come in handy for this. Okay, first of all, realize that. Okay, so first of all, let's make sure that v is a unit vector. Magnitude of v is gonna be square root of 1 plus 2 squared plus negative 1 squared. So that's gonna be what 1 squared is gonna be 1, 4 here. 1 plus 4 is 5, 5 plus 1 is 6, so square root 6. So unit vector of v is going to be 1 over square root 6 I plus 2 over square root 6 j minus 1 over square root 6 k. Okay. then what happens is, we know that now the directional derivative of f with respect in the direction of the unit vector evaluated at 1, 3, 0 is going to be the gradient of the function evaluated at 1, 3, 0 times the unit vector v. Okay, not times, dot product with that. So do you know the gradient? Yes, you know the gradient, and the gradient is from previous problem is this. Okay, now let me do this. 1, 3, 0, right? This is at 1, 3, 0. Let me evaluate the gradient of the function at 1, 3, and a 0. So that's going to be, it's going to be sine 0 I plus, this is 0 times j plus x and y is going to be 3 cosine of 0 k, right? So that's going to be 0 times I is going to be 0 of I plus 0 j plus 3k, right? So that's going to be, I think I'm getting 0, 0, 3. I hope I'm right. If I'm wrong, you fix it. Okay, so that's what we're going to use. So the gradient is going to be 0, 0, 3 dot product with 1 over square root 6, 2 over square root 6 in minus 1 over square root 6, right? So that's going to be what? 0 times 1 over square root 6 is 0, 0 times 2 over square root 6 is 0, 3 times that is going to be negative 3 over square root 6. Okay, you with me in that? I hope this is clear. So that's what, you want to rationalize it. Please be my guest and rationalize it. I'm not going to do that right now. So now suppose f is a differentiable function of 2 or 3 variables. How much time is my video? 36 minutes. I don't know. How will I even check? Oh God. That's fine. I'll go on. I need to go all the way till, what is that? I'm on the page 204. I need to go all the way till page 210. So 6 more pages or 7 more pages. Let's see how far we get through it. Suppose f is a differentiable function, of 2 or 3 variables, and the maximum value of the directional derivative is that, and it occurs when u has the same direction as the gradient of that. So what does that mean? We know that directional derivative of f at x, y, I'm taking two function of 2 variables. Okay, you can take the function of 3 variables as well. In the direction of unit vector u is nothing but gradient what of the function f at x, y dot product with u, right? Dot product is with u. So if you take the magnitude or on both sides, what happens? That's what is no, that's not what happens. You know that a dot b is absolute value of a, magnitude of b in cosine theta, right? So you don't take that. So that's going to be gradient of f at x, y times the gradient magnitude of u, magnitude of the gradient times the magnitude of u times the cosine theta, and the theta is between the gradient and the unit vector. Unit vector means what? U is a unit vector. Let me write that. U is a unit vector. Remember that. U is a unit vector means what? Magnitude of u is 1. Or sometimes I write it like this also. That's also magnitude of u is 1. Both mean the same. Okay. So that means you get gradient of f x y at x y times cosine theta. Okay. Now what happens is, the maximum value of cosine is is 1, and when theta is 0. Okay, when theta is 0. So that means you get gradient of f at x y when theta is 0, right? Theta is 0 means what? Theta is 0 means the gradient and the unit vector are in the same direction. Same direction. I hope you understood it. It's a very small proof and it's a small cube proof. Okay. So the direction derivative is maximum. Okay, is maximum. See, we are leading. We are going from directional derivative to gradient to the maximum and the minimum. Okay, we are already arriving at the maximum. Is maximum when the angle between the unit vector and the gradient is 0. That's what they are trying to say. And the maximum value is the magnitude of the gradient. Okay, so that's what it is. In other words, the maximum of the directional derivative happens when theta equals 0, and the maximum of the directional derivative of f equals the magnitude of the gradient of the function. You see that? That's what they're saying. It happens here, and the maximum is here. Okay. So now find the rate of change of f at 2, 0 in the direction from 2, 0 to 1 half and 2. So we are going to find the rate of change. I mean, in what direction does the function have the maximum rate of change? What is the maximum rate of change? So we are getting there basically. Okay, so there's really not much here. So first thing is you want to find what is that? You want to find directional derivative of the function f in the direction of the u at the point 2, 0. That's what you want to find. Is going to be what? Is going to be gradient of the function f at 2, 0 times the unit magnitude vector u, right? Are you with me on that? First, let's find the unit vector u. U is going to be 1 half minus 2, I hope you can see that, 2 minus 0, right? So that's going to be what? Negative 3 half and a 2, right? Are you with me? Now that's going to be the vector. Sorry, that's going to be the vector here. That's going to be the vector. Now, magnitude of u, is it 1 or not? So that's going to be 9 over 4 plus 4. So that's going to be, it's not 1, okay? So that's going to be square root of 25 over 4. That's going to be 5 over 2, right? So you want to find the unit magnitude vector u. That's going to be u divided by magnitude of u. So that's going to be negative 3 halves divided by 5 halves and 2 divided by 5 halves, right? So when you do that, what are you going to get? You're going to get negative 3/5 and you're going to get 4/5, okay? You're going to get 4/5. So let's find a gradient now, the gradient, right? So you want to find fx. Fx is going to be differentiate that, so that's going to be e to the y. Fy is going to be so you want to find fx at 2, 0, right? So x is 2, y 0. There is no x, so there is nothing to substitute. So you get but y is 0. You can substitute y. E to the 0 is 1. Okay, fy is going to be when you differentiate it, you get x e to the y, correct? So fy is going to be x e to the y, correct? So then what happens? So you get fy of 2, 0. So x is 2, e to the 0. So that's going to be 2, right? So that directional derivative of f with respect to the unit vector u at the point 2, 0 is going to be the gradient of the function at 2, 0 dot product with the unit vector u. So that's going to be whatever that is. I mean, you know, here 1 and 2 dot producted with negative 3/5 and 4/5. Are you with me on that? So that's going to give you negative 3/5 plus 8/5, and that's going to be 1. Okay, so the rate of change of the function f in the direction of the u at the 2, 0 is going to be that. I mean, in other words, they are saying the directional derivative of the function at 2, 0, so 1 and 2, 2, 0, in the direction of u is, where is that u is negative 3/5 and 4/5. That means here somewhere. Negative 3/5 means x is negative, y is positive, so that means like that. So in that direction is 1. I mean, this is rough sketch, so don't get too serious about it. That's the answer here. Okay, now in what direction does it have a maximum? I mean, the maximum value of that is going to be at 2, 0 is going to be the absolute value of the gradient of the function at 2, 0. So that's going to be absolute value of, what is that, 1 and 2. That's from the previous problem, right? So that's going to be square root of 1 squared plus 2 squared. So that's going to be square root 5. What is square root of 5? I mean, definitely bigger than 1. So the directional derivative at this point is 1, but the maximum, I mean, it attains the maximum value at square root 5, okay? It attains the maximum value of the directional derivative is square root 5. That's what we are trying to say here, okay? So now, this is a word problem. I'm going to leave this as an exercise for you, okay? It's cool, actually. Exercise. Should I leave it as an exercise? Let me see how much time is my video. 44 minutes. I don't know how it's gonna happen. 44 minutes, and then I want to go on to the tangent line and all that. So what's my time? 11:40. Okay, let's anyway. 2 minds. Okay, let me quickly tell you something. Okay, this is 80 times 1 plus x squared plus 2y squared plus 3z squared to the negative 1. It will really help you when you want to find, when you want to find the partial derivatives. In which direction does the temperature increase the fastest at the point that what is the maximum rate of the increase? So they're really asking you to find the gradient first. So gradient is going to be what? Gradient of t at 1, 1, negative 2, right? Magnitude of the gradient would be the maximum temperature and all that kind of stuff. So for that it's going to be txi plus tyj plus tzk, correct? So now if you want to find tx, now you're going to differentiate this. I mean, instead of using quotient rule, you can use the power rule. That makes it easier. So 80 times negative 1 times 1 plus x squared plus 2y squared plus 3z squared to the negative 2 times. Now you're going to differentiate with respect to x, so that's going to be 2x. So that's going to be negative 80 times 2x is 160x divided by 1 plus x squared plus 2y squared plus 3z squared to the 2. Okay. Now ty is going to be, again you're going to differentiate with respect to y, so 80 times negative 1 times 1 plus x squared plus 2y squared plus 3z squared times negative 2. That's the power rule. Then you have to use the chain rule. You want to differentiate this derivative with respect 1 with respect to y 0, derivative of x squared with respect to y 0, derivative of 2y squared is going to be 4y. Derivative of 3z squared with respect to y is also 0. So that gives you what? Negative 320y divided by 1 plus x squared plus 2y squared plus 3z squared whole square. I hope you're okay with that. tz is going to be 80 times negative 1 times 1 plus x squared plus 2y squared plus 3z squared to the negative 2. Z is what? I mean, now you're going to differentiate this. That's going to be 6z. So that's going to be what? 80 times 6 is going to be what? Negative 480 maybe? If I'm wrong, correct it, okay? 1 plus x squared plus 2y squared plus 3z squared squared. Okay? Remember, this is really going to get nasty, okay? You want to find tx of 1, 1 and negative 2, so that's going to be negative 160 divided by, this is going to be 1 plus 1 plus 2, 2 plus 2 is 4, okay? Z squared, 2 squared is 4, 4 times 3 is 12, 12 plus 4 is 16, 16 squared is 256, okay, 256 times 1. So that's going to be negative 160 divided by 256. So I hope you're okay with that. I have no idea. Okay, 8 goes 20 times, 8 3s 32, oh, 4 5s and 4 8s, okay? So that's going to be negative 5 over 8. I hope I'm right on that. If not, please fix it, guys. Ty of 1, 1, negative 2 is going to be what? Again, you have to do the same thing. Negative 320 times y, right? 320 times 1 divided by the denominator is same, so that's cool. So negative 320 divided by 256. So that's going to be what? 840. So that's going to be 32. So that's going to be 4. This is going to be 5. So that's going to be negative 5 over 4. I hope you're okay with that. Then you want to find tz of 1, 1 and negative 2. So that's going to be negative 480 times negative 2 divided by 256. So that's going to be 960 divided by 256. So 8 goes what? 1 times 116 to 120 divided by 32. So again, does 8 go? 1, yeah, 8 ones 15, 8 fours, so that's going to be 15 over 4. I hope I'm right. So now your gradient of t, am I on the screen yet? Okay, gradient of t at 1, 1, negative 2 is going to be what? Negative 5, 8 I plus negative 5, 4 j plus 15 over 4 k. I hope I'm right. If not, fix it. Okay. Then what's the next thing? I mean, what is the, oh god, what is the maximum increase, right? What is the next question is here? What is the maximum rate of increase? Okay, maximum is gonna be the maximum is gonna be what? Absolute magnitude of the gradient of t. So that's gonna be square root of negative 5 over 8 squared plus negative 5 over 4 squared plus 15 over 4 squared, right? So that's gonna be what? 25 over 64 plus 25 over 16 plus 225 over 16. Okay, square root of that and simplify it from here. Okay, I don't know, I'm not doing it right now, but simplify. It's okay to get decimals. So because this is a word problem, it's okay to get decimals. Okay, it's okay to get decimals. Okay. Now it's 51 minutes into my lecture. We are on to the hopefully the last topic of this today's session. That's 14.6. Okay. I want to do for now 14.6. 14.7 is maximum and minimum values. Let's find out that later. Okay. When will I do it? I have no idea. So don't ask. I hope I will be able to do it faster. Okay. So now this is what it is. Suppose S is a surface with the equation that of three variables, and let P is a point x naught, y naught, z naught. Then basically what they're saying is the equation of the tangent line is given by that. Now, why are they saying that? Let's say if you have f of x, y, z equals k, then when you differentiate it, what they're saying is dou f dou x times dx dt. Remember, they're saying f is a function of x, y, z. X is a function of t, y is a function of t, z is a function of t. That's why they're doing that. Plus partial f partial y times dy dt plus partial f partial z times dz dt equals the derivative of a constant is 0, so you get 0, right? So what did you say? So you get fx x prime plus fy y prime plus fz times z prime equals 0, right? So using the properties of dot product, you can write fx fy fz dot product it with x prime y prime, okay, z prime equals 0, correct? Now the first term is nothing but the gradient of the function, of course at x, y, z, or x naught, y naught, z naught, whatever that is, x naught, y naught, z naught, okay, times this is nothing but r prime of t equals 0, right? R prime is not a unit tangent vector, but r prime of t is the direction of the tangent vector, right? Do you see that? R prime t is the tangent vector because it's it is the derivative of the position vector is tangent vector. Derivative of tangent vector is the normal vector kind of thing. So now so that means the dot product is 0, which means they're saying really gradient is orthogonal or perpendicular, whichever way you want to say orthogonal or perpendicular, whichever way you want to say it, perpendicular to the tangent vector. That's what they're really saying it. tangent vector. Okay, if that is the case, so I mean, then what we're gonna do is is orthogonal to that. So we can write, like, I mean, these are your if you want a plane, you want to define an equation of the plane, you want to come up with a normal vector to it, right? So that these are your normals, so you can write it like that and come up with, like, I mean, remember this is in the form of ax minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Now ABC, we said they are the normals, and normals are coming out of the gradient. You see that, because the gradient is perpendicular to the tangent vector. That means gradient is at least the same as the normal, or it is parallel to the normal. So we are getting ABC from the gradient. That's what we are really saying. So your equation of the tangent plane is going to be really, instead of a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. In place of a, we write partial fx. In place of b, you get partial fy. In place of c, you write partial fy. Are you with me on that? So either that means we are saying the gradient of f is equal to normal, is equal to the normal vector. Or normal vector, or is parallel to the normal vector, whichever. I mean, I don't know what it is, but in either case we don't, it doesn't matter, because we are getting the components, and from there you can find the equation of the plane. Okay, that's clear. And when you write, I mean, I hope you remember the direction of the normal line. You write this as x minus x naught divided by a equals y minus y naught divided by b equals c minus z minus z naught equals c, right? Now we know that a is going to be nothing but fx, and b is of course evaluated at x naught, y naught and z naught, and b is nothing but fy evaluated at x naught, y naught, z naught, and c is nothing but fz at x naught, y naught, z naught, right? So that means you get x minus x naught divided by fx at x naught, y naught, z naught equals y minus y naught divided by fy of x naught, y naught, z naught equals z minus z naught divided by fz of x naught, y naught, z naught, right? That's an equation of the normal line. Okay, and the previous one was that this is not the equation of the normal line. Sorry, the direction of the normal line is given by that. And the equation of the normal, equation of the tangent plane is given by that. Okay, and that's what I was trying to say. Now, the last two things. I hope this works out. Find the equation of the tangent plane to the point here, to the ellipsoid. So that means this is in the form of fx, y, z equals k, correct? So let's find fx. That means you want to differentiate it. That's going to be 2x over 4, which is going to be x over 2, really. Fy is going to be differentiated with respect to y, so you get 2y. Fz is going to be, you're going to differentiate it with respect to z, so you get 2z over 9, correct? Now you want to find, so the gradient is this, so you want to evaluate fx at negative 2, 1 and negative 3. So that's going to be negative 2 over 2. There is no y and z component, so you don't have to substitute y and z components. X is negative 2. When you substitute that, you get negative 1. So fy is going to be, you substitute y is 1, and that gives you 2. Fz is going to be, you substitute z is negative 3, then that gives you negative 6 over 9. So that's going to be negative 2/3, right? Are you with me on that? So now the equation of the tangent plane is going to be, remember that it was fx x minus x naught plus fy z minus z naught plus y minus y naught fz z minus z naught equals 0. So in this case it's going to be negative 1 times x minus x naught. X naught is, this is x naught, that is y naught, this is z naught. Okay, minus 2 plus fy is going to be plus 2 times y minus 1 plus fz is going to be negative 2/3 times z plus 3 equals 0. So that gives you negative x, negative 2 plus 2y minus 2z over 3 minus 2 equals 0. So that gives you negative 2, negative 2, negative 2 is going to be positive x, negative 2y, positive 2z over 3. Okay. So that gives you negative 6 equals x minus 2y plus 2z over 3, right? So you want to get the equation of the line, so multiply everything by 3. So that gives you 3x minus 6y plus 2z equals negative 18 is the equation of the tangent plane to negative 2, 1 and negative 3. At to the ellipsoid. Okay, ellipsoid. I hope this is clear. If you have any questions, let me know. Okay, so now the direction of the normal line, find the equation of the normal line. I mean, we did that, right? So that was like, I mean, x minus x naught divided by fx at x naught y naught z naught, and that is y minus y naught fx at x naught y naught z naught z minus z naught divided by fz of x naught y naught z naught. Okay, that's what is the direction of the normal line, right? So yeah, and this is x naught, that is y naught, this is z naught. So you get x minus minus 2. I'm just checking if my computer is heating up slowly. Fx is what? Fx is going to be, I mean, we did that from the previous problem. Okay, these are the partial derivatives in this line. I'm just copying these values from the previous problem. Okay, divided by negative 1 and y minus 1 divided by 2. Okay, equals z minus 3 divided by negative 2/3. So that gives you x plus 2 over negative 1 equals y minus 1 over 2 equals z plus 3 over negative 2/3 is the equation of the normal line. Okay, is the equation of normal line to ellipsoid at the point negative 2, 1, negative 3. Okay, that finishes section 14.6. I hope you're clear. So bye bye for now. Namaste. Okay, with that, schlaf gut, that's German, ni hao, that's Chinese or Mandarin. Bye bye. And if you have questions, let me know. Now I hope you will watch me on your phones. Okay, don't watch on the phone, watch on the computer. Bye bye. I'll stop for here now. Just 2 minutes. I have to close my video out. Oh god, I don't know how to do it. Let me see now.